So I'm going to start off with the solution of the Vasicek model. I'm going to start off with the solution, which is luckily here. Then from here, I'm going to insert an expectation on both sides. So I'm going to say the expectation of R sub t is equal to the expectation of this whole thing, which is R sub 0 e to the power minus 18 plus b into 1 minus e to the power minus 18 plus sigma integral from 0 to t of e to the power minus a into t minus s dws. Now, I'm taking the expectation of the solution. Now, do you agree with me that this here is just a constant, and the expectation of the constant is a constant? So what I'm actually going to do, in order for you to see, I'm going to say the expectation of R sub t is equal to the expectation of R sub 0 e to the minus 18 plus b into 1 minus b into 1 minus e to the power 18, right? Plus sigma. Now the random variable here is dws. Remember, I showed you that the distribution of dws is normal here. Very important, is normal with mean 0 and variance ds. So our random variable here in our next part of our solution, which is this part here, oh, green is not a good one, which is this part here, our random variable is dws. So I'm going to leave all the terms and insert my expectation here, since that is our random variable, others are just constants. So 0 to t e to the power minus st minus s times the expectation of dws. Now this is normal with mean or expectation 0. So this whole thing will be 0. And this here is just a constant. And the expectation of the constant is just that constant. So the expected value of R sub t is equal to R sub 0 e to the minus at plus b into 1 minus e to the minus at. So that is your expected value. Now, using your solution again, now I'm going to look for the expression for the variance of RT. So I'm going to insert the variance on both sides of our equation. So the variance of RT is just the variance of our solution. I'm going to write it. So R sub 0 e to the minus at plus b into 1 minus e to the power minus 18 plus sigma integral from 0 to t of e to the minus at minus s dws. Now I'm going to separate this again to the variance of R sub t is equal to the variance. Now without wasting any time, I won't waste time here. This here is just a constant, what I'm about to highlight. This here is just a constant, which means its variance will be equal to 0. And we'll just be left with this. So we want the variance of sigma, the integral from 0 to t of e to the minus a t minus s dws. Now here, now this is the tricky part, which please remember and don't forget it. I'm begging you, I'm going to explain it now. Now, remember from your basic actuarial studies that the variance of AX, where A is a constant and X is a random variable, is actually equal to A squared. So you take the A out, but you have to square it, times the variance of X. So if you look here, the random variable we discussed, which we said ds is normal with mean 0 and variance ds. The random variable is this, right? And the rest will act like a constant, which means we'll have to take it out, but if you take it out, you have to square it. I think this is the tricky part of deriving this results. Now, which is exactly what I'm going to do here, because now I'm going to say this here. Now this and this is acting like a constant because this is the only random variable we have, which is normally distributed with mean 0 and variance ds. So I'm going to square it applying this rule here. So I'm going to have sigma squared, the integral from 0 to t of e to the minus 2a into t minus s times the variance of dws. Obviously, you know that the variance of dws is ds. So I'm going to remove this and put ds instead. Okay, so you see now you have an integral expression you have to evaluate, because I'm going to evaluate this integral with respect to s, and we have your s here. Now, I hope your integration skills are sharp. The first thing I'm going to do is to separate that exponent. So I'm going to have a sigma squared integral from 0 to t of minus 2at e to the power 2as, if you distribute here. Now, I'm integrating with respect to s, which means other things are just constants. I can take them out from 0 to t of e to the 2as ds. Now, integrating here, I'm going to have sigma squared e to the minus 2at. Then, integrating this, it's no problem. It's 1 over 2a e to the 2as evaluated from t to 0. Now I have to go down here. Now, substituting your limits, you're going to have sigma squared e to the power minus 2a into 1 over 2a e to the power 2at minus 1 over 2a e to the power 0. Obviously, anything to the power 0 is 1, so it's just 1. So I'm going to have sigma squared e to the minus 2a. Please don't forget the t. 1 over 2a e to the power 2at minus 1. Distributing this inside and take over 2a here, don't forget. Distributing this inside, so rearranging this, I'm going to have sigma squared over 2a into 1 minus e to the power minus 2at. So, answering our question here, we have got the expectation equal to, never use pink, we've got our expectation equal to this, right? And we have got our variance equal to this. Obviously, this is the expectation and the variance of R sub t. And from what I discussed earlier, where is this? From what I discussed earlier about this being normal, This means we have the normal distribution with this, mean and variance this. Now we have answered the question. The distribution is normal, and you have derived the expression for the expected value, and you have derived the expression for the variance. Now, just to warn you here, once we have determined that R sub t is a normal distribution with the expression I've derived above, the examiners can go on to ask strange things.